My name is Alanda Kriener, and today I will be going over lab number 4 regarding oscillations and the conservation of energy. In this lab, I analyzed the swinging motion of an object with a mass of 0.402 kilograms on an oscillating spring in this video. Let's take a look at the motion. In order to examine the energy of this oscillating mass, we need to use some physics. In this lab, we will utilize the physics of spring force, where the spring force is equal to the negative spring constant times the length of the spring minus its resting length, aka s, times the L hat vector. We will also use the principle of conservation of energy, where the total change in energy in our system is zero, and the components that make up the total change in energy include the change in kinetic energy, where kinetic energy is 1/2 times mass times velocity squared, the change in gravitational potential energy, where gravitational potential energy with objects close to Earth's surface is mass times gravity times change in height, and the change in potential spring energy, where potential spring energy is 1/2 times the spring constant times the change in spring length compared to its resting length squared. Like always, we will also put Newton's second law to use via the familiar velocity and position update equations as shown here. In order to analyze this video and tracker, we had to first establish a coordinate axis with the origin centered where the spring is attached to a stationary surface and the spring going in the negative y direction. I also had to calibrate the initial length of the spring, which was given as 0.7 meters, and finally, calibrate the point of mass in each frame. Then we can establish our initial conditions, knowing the mass of the object, where the mass of the spring itself can be disregarded, the acceleration due to gravity, and the initial x and y position of the object. Though the data in Tracker shows the initial time to be 0.095 seconds, I went forward with the calculations and coding as if the initial time was 0, making the initial velocity 0 for easier calculations while making note of the actual quantity. In order to make a computational model of the total energy of the system, we first have to do some math that will need to be inputted into the code, including the spring constant. After plotting the y position and time data on a graph, I picked 4 convex points on the graph to estimate the time of 3 periods. It's important to note there can be a slight variance in calculations due to the fact that the periods aren't perfect and the max and min positions vary slightly along the graph. Using these points as markings of the beginning end of 3 periods, I calculated the time of 1 period to be about 1.5 seconds. As you can see in the period of oscillation equation, the period t is equal to 2 pi times the square root of mass over the spring constant. After doing some algebraic rearranging, we can solve for k, the spring constant, and which I have found to be around 6.878 newtons per meter. After solving for the resting spring length and the spring constant, we can apply our physics principles to code to graph the total and individual energy changes of the oscillating mass. First, I inputted the mass of the spring and the initial position of the mass using my tracker data and the initial velocity of 0. Next, I entered the acceleration due to gravity as well as the spring constant and resting length we previously calculated. Next was the vector L, which describes the length and direction of the spring, found by subtracting the spring position from the mass position. The direction of L, or L hat, is then L divided by the magnitude of L, and S is the length of the stretched spring minus its initial length. Next, I entered all of the energy equations for kinetic, potential gravity, and potential spring energy that we discussed earlier, as well as the total energy E, which is the sum of all of those energies. The while loop starts by giving variables to all of their respective initial energies. I then entered the forces acting on the mass, which are the force of gravity and the spring force with their respective equations, and I added them to be the net force. Then, I used Newton's second law to code the position and velocity update equations of the mass, and again inserted the vector L, L hat, and the change in length of the spring compared to its resting length, or S. Finally, I coded the change in each respective energy by subtracting each energy equation by its initial value to get delta K, delta UG, and delta US. I then added up all of those changes in energy to get the total change in energy, or delta E. Here are the graphical results from the computational model. As you can see, the graph on the left plots each respective change in energy type with a different colored line, and the total change in energy is at 0 in the orange line. The graph on the right is the position versus time of both the x and y direction, and with the x direction in blue and the y direction in red. You can see here that their periods we are going to calculate in a minute will be comparable, but not exactly the same. So does the conservation of energy principle hold up with this lab? Well, the answer is yes. Energy conservation means zero change in total energy, or the final energy minus the initial energy is zero. If we take this point on the graph and look at each respective energy at that point, they should add up to be zero. And here they do. You can see that this point where the velocity is zero, the kinetic energy is also zero, and the gravitational and spring potential energy exactly cancel out, thus conserving energy and plotting the total energy on zero. Now let's take a look at the x and y position oscillation periods respectively. As we calculated earlier, we see that the y position period was about 1.519 seconds, making the spring constant around 6.878 newtons per meter. Using the exact same method, but choosing 4 points on the x position versus time graph, we see the period to be just slightly bigger at approximately 1.646 seconds, making the spring constant around 5.86 newtons per meter. As we saw with the computational model earlier that plotted both positions versus time, we see that the periods are very similar. To conclude, we applied the physics principles of spring force, conservation of energy, and Newton's second law to study the oscillating motion of a weight on a spring traveling in an arc. We did some calculations to determine the spring constant and resting length on the spring after analyzing the video and tractor, and we used those values in a computational model to plot the total energy and position versus time graphs of the motion.